So we've talked about binary programming before as well, and binary variables. We're going to talk about how we can use binary variables to solve a variety of different problems and interpret a variety of different situations using binary problems. So I'm going to go through three different uses of binary variables. The first use is where we have to choose a subset of some item. In this case, we're choosing k out of n possible warehouses. Right? We've got 4 warehouses, so that's our n, and we have to choose one of those warehouses to locate. So what we do is we set up a binary variable. The way we define, now remember, it's important to know how to define a binary variable. We define a binary variable as an if statement. If we do this, then it is 1, otherwise it's 0. Right? So if we locate at Georgia, it is y1 is equal to 1, otherwise it's 0. If we locate in Ohio, y2 is equal to 1, otherwise it's 0. So if you've done any computer programming or any logic, you will remember that it is if and else, right? If then else, else if. So it's the same kind of approach. So if we want to use a constraint in order to model the statement where we want to select one out of these 4 warehouses, then we will set up the constraint where we take the sum of those binary variables and set it equal to 0, set it equal to 1. So now what would happen if we would choose at most 2 locations? How would we set that up? So we'd say the sum of all the yi's, I is equal to 1 to 4, is equal to 2. Okay, shaking your head. What would it be? Okay. Let's start by why it wouldn't be it.
Binary is just 0 or 1.
Yeah, so each of these could either be 0 or 1. So in other words, think about it as a switch. Remember our mining problem? It's just the same thing. We switch off 3 of these and allow only one to take on the value of 1. Right? Now, right, this is not the constraint to satisfy that condition. What if we choose at most 2 locations? But why is it not right?
Because that's the third option. I don't know.
It has nothing to do with it being binary. It has to do with it with the so just a clue. I had an English major in this class who actually she did the best among all of my students in that year and for many years. And a lot of the logic that we see in math has. Have any of you heard of Bletchley Park? It's on Netflix. Watch it. Right? It's all these English majors who help solve the Enigma code. You've heard of the Enigma code from the Second World War? So Bletchley Park has all these Oxford and Cambridge English majors who were the code breakers during the Second World War. Because English has a lot of semantic logic in it. Right? Grammar, how you set up structures, sentences, predicates, all those conjugations, stuff like that. So what I'm getting at is the English has to be followed precisely. So we are talking about at most 2 locations, right? Not 2 locations.
Wasn't that also the imitation game?
Right. So the imitation game is the machine that was used to actually do the work of those Bletchley Park mathematicians. Yeah. 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 So the imitation game. So that's the forget what the machine was called, the Turing machine. So, yeah, so the Turing machine was actually used to, and then you have the Turing logic, which is for artificial intelligence. But anyway, so in terms of here, what do we choose at most 2 locations? What does that mean? You could choose 1, or you could choose 2. Could you choose 0?
You said it could be greater than or equal to
Sorry?
the constraint. it's y1, y2, y3, y4 is greater than or equal to 1.
Okay, so let's examine this logic. Greater than or equal to 2. That means we have to choose more than 2 locations, right?
So it would be less than or equal to 2, but greater than or equal to 1.
All right, so let's do this one. So less than or equal to 2.
Yeah.
Yep. So now this very simple 2 words here, at most, changes it and makes it this entire constraint, right? So if you recall what we did with the homework question 4 as well, and homework question 3, you have to work through similar types of logic in order to understand how to formulate the constraints over there, right? So again, we were having this discussion earlier about what is the meaning of within 10%, right? The forward hole has to be within 10% of the rear hole. So think about that, right? All right, so let's get back to binary now. So that's what it means. Now, we can also use binary variables to set up modeling fixed costs. So what happens if when we open or when we do something, we incur a fixed cost? So when we open a facility, we have a fixed cost. When we change over a line, we have a fixed cost. When we add an overtime shift, we have a fixed cost. When we put in some new equipment, we have a fixed cost. So clearly, if that decision has to be modeled, it will become a binary variable, right? Because when something happens, it triggers a cost, right? So in this case, if we locate a facility in Idaho, we incur fixed costs. So what the objective function is, it'll be the minimization of all the variable costs, right? So all the variable costs, remember our transportation problem? Just like the transportation, we have all of the SIJs. And then added to that, we would have this fixed cost element where it's the fixed cost times the binary variable. So what happens if the binary variable is 1? The fixed cost is incurred. If it's 0, there's no fixed cost, right? And the third way is where we can model dependent decisions. And this is where binary variables start becoming really powerful. And that's where the logic comes in. Because now what we can do is we can set up all kinds of dependent logic.
What does the O/W stand for?
Otherwise.
Okay.
So here what we are saying is if we locate in Idaho, if we locate a facility in Idaho, then we can ship out of that facility. If there is no facility in Idaho, we cannot ship out of that facility, right? So that is what is being modeled here. So we have our decision variable, y4. Now, the way we would model that is we have to relate. So this is our shipping function, or the shipping decision variable. x4 is how much we're going to ship out of Idaho. So we only ship out of Idaho if our y4 takes on a value of 1. That is, if we locate in Idaho, right? Now, this C is our capacity of the Idaho facility. So what is that saying? That is saying if we locate in Idaho, then the amount that we ship out of Idaho is less than equal to the capacity of Idaho, right? This amount is less than equal to the capacity of that warehouse. Now, why do we say it's either the capacity or some large number? Because if we have, 100,000 locations, we're not going to go through each one of them and program every single location with every single capacity. That's going to be very cumbersome. We'll have to write a code to do that. So instead of doing that, we just look at the largest facility and we take a number that is larger than that. And it doesn't matter, because we're going to have a set of constraints that's going to constrain how much we ship out that facility anyways. So that's why we also could use a large number. Any large number would do the same thing. Okay, so let's do a problem. Simple transportation problem. You've seen this 100 times. I solved this in the practice set video. The first two problems that pertains to homework 3 have been solved. I'll solve the next 3 once I finish this lecture. So you can see how the binary versions is done. Very straightforward. Demand is a constraint. Capacity, warehouse capacity is a constraint. We have transportation costs for each lane. So now we have a fixed cost. If we ship out of a warehouse, we incur a fixed cost. In other words, if we are going to use that warehouse, we have a fixed cost. So we add the binary variable yi is equal to 1 if we use warehouse I and it's 0 otherwise. So as I said, O/W is otherwise. So then what happens is our decision variables is fairly straightforward. We have the objective function where we add these 3 variables to, and then we have a set of 9 dependent demand constraints. Now here you'll see that I've used 500, which is just the sum of my total demands, right? Because I'm not going to ship out more than is going to meet my total demand, right? So this is one way of formulating this problem. Now, can we improve upon this problem in any way? In other words, can we simplify this problem? I'll give you a hint. Look across each row here. Or 500 Y3, yeah. You just do the sum of those. So that you would sum all of the lanes coming out from any warehouse. Because the right-hand side for any of these warehouses is all the same, right? So along the rows you'll see that the right-hand sides are all the same. So you could just combine them and you would say S11 So you could put 1500 as well, but you could use 500 as well, right? So now how can you combine the constraints further and even simplify this formulation even further? doing?
There was an example problem that we did where we used two sigmas to define how many warehouses and how many suppliers, and then we could just do the sum of 500, and then another sigma y1
Yeah, so you're just using a contracted notation for that. But I'm actually talking about combining constraints together. So combining constraints together to further simplify this.
Like S1J, that's 500Y1, S2J,
So that again is you're using a short notation for the same number of constraints. So what I'm talking about is reducing the absolute number of constraints, the actual number of constraints. So again, another clue is look at the left-hand side of all of the constraints.
You just do sum of all those S.
used to be SIJs.
So look at these two, for example, or look at these two, and these two. Yeah.
Wouldn't they just be irrelevant, those last three? They're already put in?
Yeah, they're kind of redundant. So how would you combine them in with the ones that already exist? So the left-hand side you can see is the same as this left-hand side, right? This is supposed to be a stand-in for the capacity, right? Which we already have here. So how would we combine those? We just put y1 over there, right? And then we put y2 over here and y3 over here, and we don't need these anymore. Yeah? And that's what we'll do. So what we have now is we have just S11 plus S12 So all we're doing is the original warehouse constraints, we're just putting the binary variable against the capacity. So if we have, if that warehouse is open, or we use that warehouse, then that binary variable is equal to 1, and so we're going to ship out of that warehouse up to the capacity of that warehouse. Otherwise, we set the right-hand side equal to 0, and so we're not going to ship anything out of that warehouse. Right?
So didn't it just go back to the way it started?
Yes. And all you're doing is you're just adding one binary variable on the right-hand side. I don't mean adding as in the arithmetic addition, but you're just putting one more product of the capacity and the binary variable. So now some of you are probably asking yourself, but how do we have a decision variable on the right-hand side? All right, so we use a simple arithmetic notation, operation to subtract both sides by 275y1, for example, or 50y1. So we bring the 50y1 over to the left-hand side, and the right-hand side is going to be 0. Right? All right. So let's look at a slightly more involved example where we want to use what's called a single sourced constraint, where we decide that each retailer can only be supplied by a single warehouse. Okay, so this is pretty common in a supply chain context where retailers often like to work with one supplier. Right? So here we have a single source situation. So how do we incorporate a single source situation? Where do we start? So what sort of variables do we add? How will we define them? Okay. So we wouldn't know that ahead of time. In a small problem like this, we could probably figure it out. But we want to be able to scale this to large problems where it will be impossible for us to figure this out, right? So that's why the mathematical problem is so good at it. So we want to set up the problem in such a way that the mathematical problem will be able to do that. So what are the decision variables, what are the binary variables we need to define that we could identify which that a single supplier, a single warehouse can serve each customer. So let me just give you a quick clue here. Let's say that we define the decision variable Yij is equal to 1 if warehouse I serves customer J, and it is 0 otherwise. All right? Now, what are the constraints that we would add here, given that we define these decision variables this way?
If we have more than one customer, then, like if customer 1 is served by warehouse 1, then customer 2 can't be served by warehouse 1.
So that would be how the logic would interpret, or the solution would be arrived at using. But we want to set up the structure of the constraints in such a way that we don't have to worry about how that logic is actually arrived at, because that can be done mathematically. We are concerned about how we can use the constraints in a way that would actually be able to utilize the logic of this problem, or the constraints to automatically choose that for us. Very much like solving a puzzle.
Well, if you can only use one warehouse, then I remain constant.
All right, you're onto something. Not necessarily saying what you said is right, but the logic is, the approach is correct, or is approaching the right way of doing things.
So when J changes, I also has to change.
So let's think about it in words. We want to make sure that if we are a customer 1, we can only be served by one of the warehouses, 1, 2, or 3, right? Similarly for customer 2 and 3. So if we are a customer I, we want to be served by either customer, if we are a customer J, we can be served by either a warehouse I equal to 1, 2, or 3. Only one of them can serve us. So how do we use these binary variables to do that? All right?
Warehouse 1.
Warehouse 1, 2, and 3 equals 1. Okay, so how do we write that out as a decision variable? Good. We're getting to that point.
It wouldn't be the sum of.
So use the decision variables to do that. Yes. So you're right. Either the sum of warehouse 1, 2, and 3 should equal 1 using the binary variables, right? And any one of those can be set equal to 1, right? So how do we use the binary variables to do that?
Say like y1j plus y2j
Okay, keep going.
plus y3j.
Exactly. So let's look at that. y1j plus y2j plus y3j equals 1. And this will be for all j 1, 2, or 3, right? Or written more specifically for customer 1, y11 plus y21 plus y31 equal to 1. Customer 2, y12 plus y22 plus y32, and for customer 3, so this is the general, and these are the specific. Is anybody not understanding this? Yeah. So this can either take on a value of 1 or 0, right? Any of these? Yeah? So I is a subscript for warehouses if warehouse I serves customer J. So warehouse 1, warehouse 2, or warehouse 3 for the same customer. That's why we keep the second subscript constant, J. And J could either, there would be 3 different constraints. J is either 1, 2, or 3. So there's 3 different constraints. So if you can see that the first subscript is always going to cycle through 1, 2, and 3. The second subscript is always going to be constant at the customer. So for each customer can only be served by one of those 3 warehouses. So only one of those 3 warehouse binary variables can be set equal to 1. So we are forcing, that constraint is forcing only one of those 3 warehouses to serve that customer. So these are lane binary constraints. So when we want to restrict something, we have to think about the construct, the abstract construct that we are trying to restrict. In this case, if you look at the diagram, we have lanes. So we are trying to cross out 2 of those lanes and only set 1 equal to a lane that we can ship on. So that construct gives us the clue that we want to set our binary variable as y sub ij, because that's representing a lane. Right? If it was a different construct in a different problem, then we would have to look at what that construct was and use a binary variable to represent that. If we have multiple choices and we want to only select one of them, then we have to see what that choice is set up elsewhere in that problem. So the reason I use yij here is because yij represents the construct of a lane which we are trying to restrict. Right? Yes?
So for the general equation, the J value could still be filled with 1, 2, or 3. We're just using the binary process to say 1 is yes and 0 is no.
Yeah, so J is just a mathematical notation to represent that. That could mean that constraint could either apply to customer 1, in which case all of those J's would be 1. That's why the J is constant, right? The J is representing a specific number. And that's why we say over here, for all J equals 1 to 3. This means that we have 3 constraints. for each j. And that's why we have 3 constraints over here. So when we have this constant subscript, that subscript will always take on just one value in a constraint. And you'll have the same number of constraints as the number of j values or I values or k values that represents in that particular formulation, in that particular formula.
Could we just write the first formula and that would cover all the constraints?
Yeah, so the first formula has to be written in its entirety like this. So you need to also include for all j is equal to 1 to 3, or for all j is equal to 1 to m, or 1 to r, or 1 to n, or whatever it is. So when we get into vehicle routing and facility location, because there's 50 or 60 routes, we are going to put more general notation in there. Okay, so now we are forcing one lane to be shut down, or 2 lanes to be shut down for each warehouse. So we also have to have forcing constraints for each pair of ij's, for each shipping lane ij's, for each shipping variable. So now we have to set Sij is less than or equal to 500 Yij. In other words, if we ship on a lane, then, or we open a lane, then and then only can we ship on that lane. Right? Because now we are shutting down lanes. We're restricting lanes to only one lane, one warehouse serving one customer. So we have to also combine this with constraints that are going to, because it's a dependent decision. We can only ship on a lane if that lane is open. So if we take an example, S23 is less than or equal to 500 Y23. So you can see that when we use I and j in a formula, that I and j means just one number. But this is constant for all I is equal to 1, 2, and 3, and j is equal to 1, 2, and 3. So in other words, we're going to have 9 of these constraints, right? Because we have 3 i's and 3 j's. 3 times 3 is 9. So 9 combinations of these formulations. Is anybody not getting something over here? I'm missing something here. Is everybody good on this? Yep. Because now you have to do the next problem yourself. So this is a modification of the polyurethane production inventory problem. Now assume that the cost of production is $2 per gallon each week, but you have a setup cost of $50 at the beginning of each week. So obviously we can avoid the setup cost if we don't produce in a particular week. So how do we define the decision variables over here?
If we produce, that would be $50 would be incurred, so like whatever notation of 50 would equal 1, and then if there was nothing produced that week, it would be 0.
So remember the structure of the definition of a binary variable? yi or yij or yjk is equal to 1. So it has to be equal to 1, and then the condition when, so 1 is another way of looking at 1 is yi is equal to, is true if we do this. It's false or 0 if not, right? Otherwise. So how do we put that into that structure. It has to be strictly in that structure.
It's like 50 whatever variable y I j, or not I j, but y I j. So like, I don't know, if it's 50 times the variable, if it's 1,
So
you're
you
going to
forget about 50. 50 is a coefficient, right? We don't think about coefficients when you're defining the variable, typically. So what is our decision here? Let's start with our decision.
Reduce or don't reduce.
Yes. In a particular week, right? So how do we use the structure? Y something, y subscript something, is equal to 1 if in, yeah, so yi is equal to 1 if we produce in week I. 0 otherwise, right? So we can say y1 is equal to 1 if we produce in week 1. Zero otherwise. So we have our inventory and production costs. So now remember, we have our fixed production costs over here. We have our constraints that we set up in the last Thursday, right there. What are the dependent conditions that we have to model here?
If we run the factory enough,
Sorry?
if we run the factory, if we produce the polyurethane enough,
Okay. So what will happen if we run the factory?
it'll be a fixed cost of product.
Okay, but operationally. Sorry?
Is it $2 per product?
We'll produce something, right? So in other words, what decision variable are we going to influence? The amount we produce. So that's a dependent decision, because if we don't produce in a week, we don't run a production in 1 week, we're not going to produce anything in that week. So the decision variable of production is going to be dependent on whether we run the production line or not, right? So we need to model that dependent decision. So how do we model that dependent decision? We produce in a week only if we run a production line or run a production in that week, right? Remember, we shipped on a lane only if that lane was open, right? There was a dependent decision over there. So now we have a dependent decision. We will get some production only if we produce in that week, right? So our decision variable for production is P1, right? So we produce in a week only if what? Only if we run the production line in that week, right? So how do we relate the two? So I'm just going to add up all of these, our total demand, because we could conceivably have our total demand produced in any particular week. The amount we produce has to be less than or equal to 600 times yi, right? Just like we saw, the dependent decision.
Would you not add the inventory?
Okay, let's think about that. So our inventory is dependent upon how much we produce in a week, right? So that's independent of the production. But that's a good thought, because now how is our inventory affected by whether we produce or not? If we produce in a week, if we have enough, it gets carried over to the next week. But then that's going to affect how much we produce. Right? It does not affect our inventory, because our inventory is what's left over at the end of the week. So that's a good point. And so you need to think about that. What happens to the inventory? If I produce in week 1, and if I produce enough for the next week or the week after that, then that's just going to go into the inventory. It's not going to affect whether I produce in the next week or not. It's going to, it's not going to be affected by whether I produce in the next week or not. It is going to affect what I produce in the next week or not, because that's going to determine the amount. So the P is the one that needs to be, is the one that's dependent upon whether you produce in that week or not. It's not the I. Okay? Yes?
Why would you produce 600 a week?
So I'm not saying that I'm producing 600 a week. I'm just saying that is the upper bound of how much I can produce. Because how much I'm producing a week is actually influenced by the original constraints that we formulated. Right? Conceivably, we could produce more than that, right? Because what this formulation allows us to do is to produce more and carry it over in the inventory. And so we are taking into account the inventory that we also can carry. Right? We could also make this number 1 million. It does not matter, because this formulation over here is going to influence how much we actually accurately produce. And then we have to restrict the variables where y1, y2, y3 are all binary, or another way of saying it, belongs to the set, or bounded set of 1 or 0, and sometimes you see the notation written as 1 and 0 in curly brackets as well, so whichever one is easier. So this is a defined set, this is a bounded set, so mathematically it's more or less the same thing in this context.
Is the p-value how much we produce?
In a week, yes. So that's from the original formulation that we did on last Thursday. We formulated the production inventory problem. So this is just a modification to say if we have a fixed cost. Now clearly we're doing very small problems, but you can easily see how this scales up to very large scale problems. So the beauty of binary variables is they can be applied to all kinds of settings. For example, if we had a shift and we had different times of the day or different days of the week where we wanted to produce something, or in this case, ship out of a warehouse, we only wanted to employ our shifts on days when we actually had to make a shipment. For example, there might be a setup cost on a day when we want to ship out of a certain warehouse or a certain location. So now the concept of pop-up warehouses is pretty common. So okay, we have a pop-up warehouse somewhere only if we need it, right? So how do we know when we want to ship out of that warehouse? And more importantly, what is the capacity that we want to ship out of that warehouse, right? How do we model that? So those two elements of how much we want to ship and when we want to ship can be modeled using binary variables. So we can say that we can define, just if we have days of the week, we have 7 binary variables. Y1 is equal to day 1, Y2 is equal to day 2, Y1 is equal to 1 if we ship on day 1, 0 otherwise, right? And then we could have a capacity warehouse, capacity variable for that warehouse, just like we showed earlier, where you have less than or equal to or greater than or equal to. But then if you add a y1 to the capacities, now this allows you to say that I can do this on a particular day. If it's not optimal to do it on day 1 or day 2 or day 3, then it's going to choose for me the optimal day to actually do it for me, right? So for example, if we have a trailer that is getting fed by other trailers in a pop-up warehouse, and then we want to ensure in the problem that that trailer has to be 3/4 full before it leaves, and we don't know which day that is. So we assemble enough of freight on every day where the drivers come and unload their freight, and then when we know we have enough of freight, then on that particular day we leave, right? So that is where we now have people who come in and load the trailer, and then the driver can take off. So that's all of these small nuances can be added to these problems and add additional complexity to them, and we'll see how we can do this even in other future problems. Another really common problem that is used a lot in transportation, especially in, and you did a version of that in homework 3, well, I say a version of that because it was sort of an unconstrained knapsack problem. But what we have is a knapsack problem where you have certain items. So this problem was developed in the early 60s. So the idea behind why it was called a knapsack problem is you have a backpacker, and the backpacker has a limited resource, the backpack, in which he or she can take a large number of items for their survival or for their comfort or for helping them navigate on their trek. And each of those items have a certain value, utility. But there's also a volume and a weight capacity that the backpacker can carry on his or her back, right? And also volume and weight capacity of the knapsack itself. So now you have a number of different items, X1, X2, X3, that have different attributes, volume and weight. You have a capacity of a knapsack. If you think of a truck, it's like a knapsack, right? It has a fixed volume and a fixed weight capacity. So you have all of these different items. They could be pallets, they could be packages. And we can now also define the decision variable where we say yi is equal to 1 if we load item I, 0 otherwise. And now we can optimize. So think of yourself as a FedEx, think of yourself in a FedEx facility. You have 3 million items, and this integer program goes through these 3 million items and tries to solve them, depending upon which lanes the trucks are going to. How do we now fill up this truck optimally? Or if you're in a warehouse and you're trying to serve a customer, or you're trying to serve multiple customers, how do I manage all of these items? If you ever encounter a truck load item, a truck loading software, that is exactly what the truck loading software is doing. It's solving a knapsack problem. Now, knapsack problems are also used in warehouses for optimizing space utilization. So you've seen videos of these robotic warehouses, right, that we've seen. So how does a robot know, and how does the WMS know? Next semester we're going to talk about WMS systems. We're going to get more into the WMS systems, where we actually have to measure the cube, the volume of each package, and weight. There's actually a machine that you put it onto that machine. It takes laser measurements and gives you the length, width, and the height, the depth of the item, and then takes you the weight of the item, because it has to put it in a particular part of the warehouse, right? So how does the WMS software know how to do that? It's a knapsack problem, because if you think of each shelf and each bin location, so you have aisles, you have racks, and then you have a bin, right? So you've been to IKEA, right? You've bought stuff at IKEA. It's a 3-code identification of where that is. So in that 3-code identification, how do I know what stuff can fit in there? It's a knapsack problem, because each of those items is a binary variable that the WMS software can solve and find what is the optimum location. Of course, there's other business rules also, because, for example, you don't want to keep glass lamps next to big wooden crates that people are going to come and load with, large forklift trucks. So there's other business rules, because you want to be able to collect packages together, not collect one package for one item from one place, go to another place and collect the same item in another package. So, but that's the basic logic of how you solve. So binary variables can be very, very powerful, and some of these large-scale supply chain network design uses a lot of binary variables. So how do we now model this in Excel? So I think it's better to demonstrate it like this. So what I'm going to do is I'm going to add so we have y1, y2, y3. So these are the S11 variables. So this is your standard transportation problem, right? Now all I need to do over here is I need to add my binary variables, y1, y2, and y3. Yep. So if I go back to my formulation, the reason why I want to simplify this is because it really simplifies my Tableau. Okay, it makes it very simple to put into my Tableau, because if I had to use this formulation, then I would need to have another 9 additional constraint rows put into my Tableau. Here I don't have to add any additional constraint rows. I just have the existing constraint rows that are put in there. So if I go in for the first one, all I have to do is this is going to be 0 here, and that's going to be -50, right? Is everybody with me?
No. Oh yeah. Yeah.
Yeah, because what I have here is what is this doing? So what I do is I subtract 50 from both sides. Yep. In this case, I subtract 275 y2 from both sides. Yep. Simple arithmetic operation. I'm just balancing it out. Or if you can think about it, I'm just transferring one to changing the sign. So then this one is going to be minus 275, and this is going to be 0, right? and this is also going to be minus 275, and that's going to be 0. And then here what we have is just 100,000. So I'm not going to add any formatting as yet to this, but you can imagine you changing the formatting to extend the blue line over here, to extend this blue line all the way there. And of course, this red line is going to be extended all the way here to make sure that these also are decision variables. Yeah, so we changed the sum product. And then you would copy this all the way up. Right? So now the problem is changed to accommodate your binary variables. So here in this case we only have 3 binary variables. Now if you also look at the single source part of the problem, there's going to be 3 plus 9 or 12 additional constraints that you have to add over there. So the 3 constraints for each customer to be single sourced, plus the 9 lane forcing constraints, right? So you're going to have 3 plus 9 additional, so 12 additional binary variables that you're going to add. So you're going to extend this 9 more columns and extend this down 12 more rows. Okay? All right. So now all you have to do is go into Solver. So the objective function is already set to O11. We are set to minimize. Now we have to change the changing variables because they only extend up to k. So we have to change them all the way up to n of 14. Then we want to make sure that we change these. So this is set up right. These 3 cells is equal to those 3 cells, and the first 3 cells is less than or equal to the second cells. It's set up to make unconstrained variables non-negative, and then are we forgetting something? Exactly. So we have to add another constraint to say that these 3 variables are binary. Okay? That's all we do when we have binary variables. Now once we've done that, then we can hit solve.
You have to make those
Sorry, which one?
The binary ones can actually be integer.
No, the binary are automatically just considered integers. So now you can see that this is not exactly binary, so I'm going to go back and check. Sometimes these options, okay, so what happens sometimes, and now this is a good case to show you this. I don't know why my cursor is not working. So sometimes you'll find that the binary or integers don't work well. So it's because you might have checked this box, or the box might have come checked by default to say ignore integer constraints. So just click on that, click that off, say OK, and then resolve this. And then say OK. So now you can see that only 2 warehouses are used. And it makes sense why those 2 warehouses are used, because you're trying to minimize the opening cost, so you don't want to use all 3 warehouses, but those 2 warehouses are able to satisfy all of the demand, right? Yes?
Can you upload this version
So your version already has it in solved, so I've already solved it over there.
with the binary
Yeah.
components? Yeah.
It already comes in solved. Yep. So you don't, I mean, you can, I just use that to show you how to walk through how you do it.
Sure.
Any questions? So you would set it up in the same way. If I had to add the single source constraints, I would just add 9 more variables over here. I would have 3 more constraints for the single source constraints and 9 more constraints after that, so 12 constraints in total. Those 9 constraints are the forcing constraints, right? And then you would do the same thing where the right-hand side would always be real numbers. All the decision variables would be on the left-hand side, and then you would put the constraints into the appropriate columns for each row of the constraints. Yep. And then the sum products are the same. It's just that entire row of coefficients all the way up to the last variable, and those same sum products just go all the way down. Any questions?